Hello, welcome to Noise Control and its Management. Today is the fourth day of this course, and what we plan to do today is complete the example problem which we had set up yesterday. So, what we had set up yesterday was that there is a tube with a diameter of 161.5 millimeters, and it is attached to a side branch muffler, which is essentially a closed short tube, or not short, some length tube. Air is flowing through it, the properties of air which is flowing through it are given, and we want that this side branch should have its maximum performance at 250 hertz, and it should be the shortest possible tube. So, with these conditions we want to find the transmission loss in this system, and we also want to figure out the transmission loss at 177 hertz. So, this is the overall problem scope. So, first we will compute LC. Okay. So, calculation of length. So, LC. So, remember in short tubes or in these tubes there could be several modes. So, one mode could be lambda over 4 is L, another could be 3 lambda over 4 is L. So, the tube will be shortest when when lambda over 4 is equal to L, that is the condition which is satisfied. So, LC equals lambda over 4 at what frequency? 250 hertz. So, lambda at 250 hertz is what? Its velocity of sound 343.8 divided by 250. Okay. So, LC equals 343.8 divided by 4 into 250. So, that gives me LC equals 0.3438 meters. Now, remember this is LC, but our tube is like this. This is a closed end. Now, we had said that LC equals L plus LA plus LB. Now, because there is a closed end here, the effect of mass on the other side is 0. So, I can ignore LB, but there is some additional mass here which also adds to the length of the tube. So, I have to compute LA, right. So, LC equals L plus LA, and remember this tube is attached to this pipe, and this pipe acts as a flange. It acts as a flat surface, right. It acts as a flat surface which acts as a flange. So, this additional increment due to the presence of flange is equal to 8a over 3 pi. So, this and LC is 0.3438 equals L plus LA, and what is LA? 8a over 3 pi, and A is the radius of this pipe. So, 2a equals, we are given 54.8 millimeters. So, A is 27.4. Okay. So, this gives us as L, which is the length of the tube will be. So, if I do all this math, I get L equals 0.3205 meters. So, if I attach a 32.05 centimeter long tube in this big pipe, it will suck in a large amount of sound energy at 250 hertz. Now, how much is it going to suck in? That is now the next thing we are going to compute. So, we know that to compute transmission loss, we have to calculate this parameter 1 over 80, and to find 1 over 80 we have to calculate sigma, we have to find RS, we have to find all these things. So, we will just do these things one by one. Okay. So, first we will calculate the effective viscosity. So, effective viscosity equals mu times 1 plus gamma minus 1 divided by gamma times Prandtl's number, and if I do all the math correctly, I know all the values on the right hand side. I know viscosity which is defined, I know gamma which is 1.4, I also know Prandtl's number. So, this works out to be 25.46 times 10 to the power of minus 6 pascals seconds. So, the next thing I do is I compute sigma. So, sigma is the attenuation coefficient of in the air which is inside the pipe, which is attributable to the viscosity, effective viscosity. So, that is equal to pi mu s. So, is it mu s or mu c? What did we define it as earlier? Oh, I said mu c. So, I am sorry, I should call it mu c. So, it is mu c times frequency of interest, which in this case is 250 hertz divided by rho naught divided by A times C. So, if I again plug in all the numbers, I get this as 0.0137 meter inverse. Okay. Third thing, S equals the cross sectional area of the pipe. So, it is pi by 2 into its radius square 0.1615 square, and that is equal to 0.02048 meter square. S is this cross sectional area, if you remember. This is my S. Okay. So, I have computed mu c, sigma s, all these things have been calculated. One thing which I have not calculated is R s. And what is R s? R s is the specific acoustic, it is the acoustic resistance attributable to the presence of mesh, if you remember. Now, in this case we do not have any mesh. So, R s is equal to 0. So, we can just drop that term. Now, let us also find out K L, because we have to find tangent, actually K L C, we have to find K L C. Okay. Now, I do not have to do all that calculation. I had assumed that at 250 hertz, the mode which will exist in this tube will be something like this, right. That is how I said that lambda over 4 equals L, and that is how I calculated the value of L, right. So, corresponding to this thing, if I calculate KLC, it will be pi over 2. It will be pi over 2. So, you can again do the calculation and you will find that KLC is actually pi over 2, and which means that tangent of KLC at 250 hertz is what? Is very large, it corresponds to infinity. So, when it corresponds to infinity, 1 over AT is equal to what? Is that simplified expression 1 plus pi A square by 2s divided by sigma L plus R s by rho naught C, this whole thing square. And in this we know everything, all the terms are known, and if I compute this, this works out to be 199.28. We know everything in this thing, we know A, we know S, we have calculated sigma, we know L, R s is 0. So, we know everything in this thing. So, this comes out to be 199.28. Okay. Or you can say that AT equals 1 over 199.28. And remember, what is AT? It is equal to W out divided by W in. So, what this tells us is that if 199.28 watts of sound energy is going into the tube at 250 hertz, only 1 watt is coming out. So, it is working as a very efficient sound absorber. So, it is doing a very good job as a noise control mechanism, and the transmission loss for this is what? 10 log 10 1 over 80, and if you put in the value of 80 as 199.28, you get 23 decibels. So, this is at 250 hertz. This is at 250 hertz. Now, let us do it at 177 hertz. So, we were told that we should figure out what is the shortest possible tube. We have done this. The tube works at 250 hertz and we have computed the transmission loss. The other thing we have to do is compute transmission loss at 177 hertz. Now, look at this entire expression here. Mu c does not change with frequency, sigma does change with frequency. So, we have to compute sigma. This is one thing we have to recalculate. The other thing we have to compute is, we had used this simplified expression because tan KL was in infinite. So, those things, but instead of using this expression, we will now use this long expression for computing 1 over 80, because at 177 hertz tangent of KLC will not be maximum, it will be some number which will not be infinite. So, we have to recompute sigma, which is frequency dependent, and we have to incorporate the effect of tangent square KLC. So, that is what we are going to do. So, at 177 hertz, 177 hertz, first thing we do is, what is KLC? So, LC is already known and K is wave number. What is wave number? 2 pi divided by lambda times LC, and this is equal to, what is the wavelength? Wavelength is C times frequency and times LC, and in this case frequency is 177 hertz. So, we plug in this, we already know the value of LC. If we do all this calculation, what we get is 1.111 radians KLC, and now we again calculate sigma. So, sigma equals pi mu c f over rho naught divided by A times C, and this works out to be 0.01153 meters inverse. So, sigma L equals 0.01153 times 0.3205, and this is equal to 0.003695, and pi A square divided by 2s we had already calculated earlier. So, I am going to rewrite that number again, is this is equal to 0.05758. So, 1 over 80 for this situation equals sigma L plus R s divided by rho naught C plus pi A square by 2s, the whole thing squared, times tangent square K L, actually it is KLC, plus 1 divided by sigma L plus Rs by rho naught C square tangent square KLC plus 1. Now, again this term is 0 and this term is also 0. All other terms we have calculated. So, all it is just a question of plugging in all other terms and computing the value of 1 over 80, and if you do all this math correctly, what you get is 1.01583. Okay. What does that mean? What, or if I take its inverse, then 80 is equal to 1 divided by 1.01583, and 80 is what we have defined is what? W out divided by W in. So, at 177 hertz, if I throw in 1.01583 watts of power, 1 watt comes out. So, only 0.01583 watts is getting absorbed by the side branch muffler, but at 250 hertz, if I throw in 199 watts, only 1 watt comes out. So, again what this shows very clearly is that this side branch muffler, if I use just a simple closed pipe, it works very well at resonant frequencies. So, this is the point which has to be again understood, it has to be understood again and again, and in this case the transmission loss is equal to 10 log 10 1 over 80, and that if you do all the calculations, this is pretty poor, 0.1 decibels. At 250 hertz it was 23 decibels, at 177 hertz it is very low, it comes down to 0.1 decibels. So, this I think gives you the overall picture of a side branch muffler, and tomorrow we will very quickly cover a third flavor of side branch muffler, and then we will go to other types of mufflers which are reactor, this expansion chamber mufflers, where there is no side branch. So, that concludes our discussion for today, and I look forward to seeing you tomorrow. Thank you.